Before we even think about connecting a voltage source to charge the cap at negative time infinity, the cap has been connected to the resistor. There's 0 volts on the capacitor. When you finally make this circuit at some time at negative time infinity, we close the switch. The cap voltage cannot change, at least for an instant. The cap voltage is still 0 volts at negative time infinity when we close the switch. Now the switch remains closed for sufficient time for the capacitor to charge to the voltage of DC voltage Vs. Later then we open the switch. When we open the switch, we conveniently call this time T0. This is the start then of our positive time. At time T0, when the switch opens, the cap has a DC voltage of our V sub S source voltage. Now at time negative infinity, when you first close the switch and the voltage remains at 0 volts, because the cap voltage cannot change instantaneously. Situation is important when we do a series analysis, so we can evaluate the lower limit of integration. We're going to have after T0 up to time T, we're going to have a source-free circuit because there's no forcing function, and then we're going to have the natural response as the capacitor discharges and dissipates through any load. This is the node equivalent for parallel analysis of the RC network, and we're also going to analyze a series. This is going to be much easier. The node series equation writing is going to be a little tricky, but I'm going to do it. All of the cap voltage is embedded inside of Vn. We don't even need to know what the cap voltage actually is from a function. It could be a simple function. It might be a little complicated. We don't even know. We don't even have to care about what it is here when we use node analysis on this simple circuit. And when we see the actual cap current is I equal C times the differential. Actually, Vn is cap voltage, Vn divided by dt, differential time. This is it. That's the equation. This is going to be the node analysis as suggested by the book, and they insist to use a current that exits the node is going to be positive, and of course any currents that might enter the node will be negative. They're focusing on currents that exit the node because we charge the cap to a positive negative voltage, as we see here, which means Vn is more positive than the reference. So it's only natural our equation is going to be written with a lot of plus signs in both cases. This plus and this plus represent the current exiting the node. Vn over R is positive, passive sign, positive Ohm's law, because the current exiting enters the plus terminal, positive, passive sign. Here the current exits, enters the positive terminal of the cap, and that's the positive passive sign for the cap. And so I didn't even bother to show those extra plus signs. Now the 0 over here is because we don't have any current sources pushing current into or out of the node, so it's just 0. If there had been other components, branches with voltage sources, some of those might be exiting Vn, some of those might be entering Vn. We would still write everything on the right side. These, of course, are plus for exiting. It's possible a voltage source is pushing current into the node, and that would be, of course, a negative. It still is probably going to meet the passive sign convention for positive Ohm's law. Typically, that's how it ends up. I'll repeat the analysis here, but this time I'm going to use the standard way that the books always suggest to do it. Current that exits the node is always going to be positive. Any current that enters the node is going to be negative. And we also assume that Vn is more positive than the reference. Kind of like when we draw mesh arrows all clockwise. We don't really know the whole flow is going clockwise, but we just use the clockwise direction for our mesh arrows or loop arrow. It's just a standard way to do it. Makes the equation writing more similar for every circuit we do, and it helps to minimize errors. So here we assume Vn is more positive than the reference node. We don't really know that it is more positive. We won't know that until the circuit is fully analyzed and we start seeing some numerical values. And again, the equation, we still write everything on the right side. It's the writing of the initial equation is always the big deal. Here's a slight manipulation to get it into a form that we can eventually use to write the classic exponential equation for a simple RC network. Again, yeah, there are implicit plus signs I didn't show because, again, we're still working with a positive passive sign for the resistor and a positive passive sign for the cap. I didn't even bother to show the plus sign for this current exiting the node because it's really not necessary. But then again, sometimes implicit signs in the books, obfuscate. Sometimes they obfuscate the equation writing by not showing everything in the books. On frame number 2, I didn't point that out when I had over here the all underlined when you did the node analysis. All of the cap voltage is equal to the node voltage. There's no resistance in the cap branch, so that kind of consolidated all of the cap voltage as the node voltage. That's the easy way to analyze a circuit, is node analysis. But here we're going to view this as a series network. And this time, finding the capacitor voltage isn't going to be as simple as the node voltage as was done with the parallel analysis. We already kind of know that there's an initial voltage on the cap because we charge it up with a Vs. At time t0, there was a DC voltage on the cap, which is easy to synthesize as a plus-minus voltage source in series with the cap. If we look at the ICE for the cap and then rearrange to solve for the capacitor voltage, we integrate both sides, and then we can manipulate this integral because VT, VO is VT minus VO, VTO. We can move VTO on the other side, so it's going to be plus over here. This integral we leave alone. We don't have an explicit function for I. It's a function of time, but we don't know what it is, so we can't really evaluate this integral at all. But this one we can, and we see that this is the full voltage definition of the capacitor. It's the capacitor voltage plus the DC voltage, something that we didn't encounter when we used the node analysis. So we don't get that simple consolidation of node voltage is equal to the entire cap voltage. Mathematically, this is what it is. And so when we use this, we can write our KVL equation. We can either traverse or use other techniques, which again is beyond the scope, but I do show another way we can write this simple loop equation using total V rise equals total V drop. VO, of course, it's V rise. Going across the cap, negative, positive, is also a V rise. We'll get back to that. Plus, minus, we're going to have a V drop. And of course, I say right here, cap, current, the current I, the loop current, mesh current, is entering the bottom of the cap. It's entering the negative side here. So it's negative passive sign. We've got to put that in there. Always got to stay alert about the passive sign, because when we write KVL equations, and even when we're doing a V rise equal V drop, there's still a positive Ohm's law here, and this is a negative passive sign for the cap. Under the positive side enters the negative side. And this, again, as I say here, is the most important part, is to write the initial equation of the circuit. Once we get this, the rest of it is still not easy, but this potentially is the most difficult part. And this is the correct equation. This is the full cap voltage, which was basically unspecified when we did the node analysis. I'll back up for a moment and look at the another way to write the cap voltage mathematically is to look at the entire interval from t to negative infinity time, and we have two intervals from to to negative infinity and t and to to t. So we have two limits of integration. Both of these integrals account for the entire time from t, positive t, to negative time infinity. We can evaluate this first integral at negative. This is a 0, so all we're going to be left with is VTO minus 0 is, well, 0, so we got VTO. This integral we can't evaluate at all. We don't know what I is. It's a function of time, but we don't know what it is yet. So once again, we have this voltage at time TO, the initial condition on the cap. And this voltage, of course, is easily synthesized as an independent voltage source that was shown on the previous frame. This equation here, it was written directly using node analysis, and the next frame we're going to look at the KVL equation, and we're going to put it into this same format, because both analysis approaches, node and series analysis with KVL, are both valid. Here is the original KVL equation from 2 frames ago. This really is the preferred format of any KVL equation. Take the derivative of both sides, derivative of a constant, 0. The derivative of this integral is 1 over c times I. I is still a function of time. And the derivative here, we have r times di over dt. We don't really know what the function for I is as a function of time, but we do know in a simplified way that I is equal to v over r. So we can substitute that in the equation, and just a little bit of manipulation, right back to the same equation that we wrote so easily with node analysis. We can separate the parts and integrate both pieces, and we end up with the classic exponential form. Mostly mathematics, calculus here. The electronic books don't do enough physics. There's always extra things going on. The electronic books do not have a chapter on reviewing how to solve physics problems. You're going to get that from a good calculus book. or a physics book, but you're going to have to do the calculus anyway. So that's the end result of this RC analysis. Again, R could be a bunch of resistors equivalent. C could be more than one cap that we combine to make an equivalent capacitance. And of course, this leads into a switched capacitor circuits and the unit step function. That's typically comes in the next chapter.